because the reverse can always happen. So you always have this plus this forms this, except for sometimes it goes backward too.
We're recording.
So you always have a two-way street with a chemical reaction, and the reverse can actually happen. So occasionally a reactant will be reformed when products react in certain circumstances. So you almost never run out of reactants entirely unless you take serious measures to force the reaction to completion. So if I really wanted to force a reaction to completion, I have to consider what's my enthalpy, what is, Gibbs, make sure that it's favorable, and what kind of temperature and pressure situation would encourage my reactants to react fully. Then things like stirring, crushing, all that stuff to make sure that the last few encounter each other after all. And in some circumstances, you really don't want your rate or your reaction to go to zero, or you want it to take a really long time, so you can manipulate the temperature, pressure, circumstances to, that you can leave the surface area small so the reaction is slower. And today we're kind of going to play with catalyzed reaction to see how we can manipulate rate based on temperature and concentration. But when you find the rate equation, you're really only ever going to find an instantaneous rate because concentration is always changing during a reaction. And if it's always changing, you can find a constant as long as you keep your temperature the same, but you're never going to find anything outside of the instantaneous rate because the next second the concentration has changed. That means that when you look at the equation, does this work? No. So if I just have two reactants, let's say, this K will stay the same as long as my temperature stays the same, basically. But this rate has to be instantaneous because every second the concentrations are changing. That's going to change rate. And there's really not much you can do about that. That's just how reactions proceed. So you can find instantaneous rate. And that can be useful sometimes. But I don't know, I never really used it a whole lot, instantaneous rate. To really study kinetics, you need a lot of calculus. Because you see that these things are on a curve, they're changing all the time. So anytime you want to know more about the rate, you're really going to need more math than what you have now, and that's fine. Just keep going and you'll get there. Let's see. So I just said that this equation holds true only if you hold the temperature constant, but you don't see temperature in there. So just to beat the dead horse that we talked about last week, why is it that this depends on temperature even when temperature is not a factor in the equation?
Because K is the constant for that temperature, but then if the temperature changes, K changes.
Right. So you can actually find K experimentally. I mean, you can observe the rate and know the concentrations that you put in, find instantaneous rate, calculate out K. But K is actually this. Not an equation I memorized or use frequently. All right, so this is a natural log, which you may or may not have had. You don't need to know this or anything, but I want you to see how K actually does depend on temperature. R is like PV equals nRT, that's that R. And temperature appears here in the exponent. So you can expect that K is going to change somehow exponentially as it varies with temperature. And it seems likely that that math is somewhat complicated, and you don't actually need to know this for the test, but K definitely depends on temperature in an exponential relationship. So that's the Arrhenius equation, and I'm sure you will cover that in college. But K depends on temperature, and there is a test question for you guys about why the rate equation doesn't involve temperature, but yet you can't change the temperature without changing the rate. So definitely K factors in temperature when you actually see where K comes from. I don't know where my notes are. Your book teaches you that concentration and temperature and rate vary with each other in a predictable way, which is so not always true. But there are problems that you do this week that involve rate doubling for every 10 degrees Celsius increase in temperature. You're going to see how rate definitely is affected by temperature, and rate in almost all reactions, but not all, increases with temperature. And you'll see that very clearly with the lab activities, I really hope. But that simplistic relationship between temperature and rate is not really true in most reactions, I would say. So I wouldn't bet the farm if you're playing with expensive chemicals on doubling your rate with 10 degrees Celsius increases. I would carefully experiment with the given reaction at very specifically measured temperatures before I decided what was happening to the rate. And you'll see today how well it goes. Not looking more good. So today the reaction that we're going to do in lab is catalyzed. Last week we talked a little bit about catalysts. Some of you weren't here, so we definitely want to talk a little more about catalysts. And let's see, how shall we do that? We know that there are two kinds of catalysts. I'd love to write them in two different colors if two are available. All right, so let's review what happened last week. I just collected your labs. Last week we looked at a situation where hydrogen peroxide was being decomposed. Hydrogen peroxide decomposes under normal room temperature sort of circumstances, but it decomposes very slowly. So as long as you don't expose it to light and heat a lot, some of it will decompose, but it will still clean your cuts or take out your stains and do what you need it to do around the house. Even though its Gibbs is favorable toward decomposition, it's a very slow reaction. If you catalyze that decomposition with yeast, it goes very, very quickly. So first of all, let's consider what a catalyst is to begin with. Somebody is very determined. If your mom wants you, that is important. So what is a catalyst?
It speeds up the reaction.
Okay, a catalyst speeds up the reaction, and how does it do that?
By, becoming a reactant.
Sometimes.
And then if it becomes a reactant, it then becomes a product in the end.
Good. So which kind of catalyst does that?
Homogeneous?
A homogeneous catalyst does that. So I want green. Okay. So Grace says it becomes a reactant.
Wrong one.
Can't read. But is reformed in the end. I should. Not reformed in the religious sense, but actually reformed. Becomes a reactant, but is reformed in the end. What do we know about homogeneous catalysts besides that?
Same phase.
Same phase. They have to be the same phase as at least one reactant. Okay. So these guys actually participate in the chemical reaction, and then they're reformed in the end. When you're asked to identify one of these on the test, what you just want to do, you'll have like And so if you have multiple steps, and this is the first of those steps, and this is the last of those steps, which guy is the catalyst?
X.
X is the catalyst. How can you tell?
Because it's a reactant in the first order and a product in the second.
Right. So essentially what happens is you never decrease in concentration because even though it's being used up, it's reformed. So it's always present, always there to provide that pathway for the reaction to be faster.
Another overall definition of a catalyst is something that doesn't get used up.
Right, so the overall definition of a catalyst never gets used up. It's not used up. It increases rate. But how does it increase rate? I mean, we know each of these functions in a specific way, but overall, how do catalysts increase rate?
By cutting down its activation energy.
Exactly. They increase rate by reducing activation energy. Oh, okay. Nah, I'll just write it out. Alright, so we're going to increase rate by reducing activation energy. And we'll kind of look at some rough energy diagrams for that too. How about a heterogeneous catalyst? It doesn't participate in the reaction like this, so how does it speed up a reaction?
It draws the reactants closer to each other so that they can collide more quickly and make the reaction go faster.
So it attracts reactants to itself. That means that they're also closer to each other, so you have like kind of a pool of extra concentration, and we know concentration increases rate. And how might you identify it?
It would have a different phase.
Right, it's not going to be the same phase.
And do they tend to be metals that are being catalyzed?
Yes, other than yeast, frequently platinum is a great catalyst for tons of stuff. Frequently your heterogeneous catalyst is going to be a metal because the metal is going to attract certain chemicals to itself, especially ionic things, because metals tend to hold a charge occasionally or have charged areas, and so charged ions are going to zoom over there and hang out, and then that can increase their concentration in a certain area. Today, we're going to catalyze a reaction where the reactant and the catalyst are aqueous. So what kind of catalyst are we going to be looking at?
Homogeneous.
It'll be a homogeneous catalyst because it's aqueous, just like one of the reactants. Well, it's the only reactant. Catalyst. So let's look at a couple rough energy diagrams. And I'm going to make you guys draw them. So, Micah, come on up and draw, well, not burning yourself on boiling hot water, moving cord away. But would you draw a rough energy diagram that is a endothermic reaction? And Aaron, will you draw one right under it that is an exothermic reaction? Endothermic. Just as a quick review, you can drag all this stuff out of the way if you'd like so that people can figure out. Okay, so he's got an endothermic reaction. He labels his axis. Yay. That should be, no, we don't want time, we want enthalpy on that axis. Okay. Alright, so how can we tell he's got an endothermic reaction there?
Because it starts low and ends high.
Starts low. So the energy of the reactants is low, the energy of the products is higher. so that means it took in energy. So did that reaction feel cold or feel hot to an observer?
Cold.
Oh, cold. But it's really taking in energy. That can be kind of counterintuitive. So then Aaron's got another reaction, exothermic. You guys chose such nice colors too. Cold, hot. You can label your axes and put exothermic. Okay, so Aaron has an exothermic reaction. Starts out with high energy reactants, ends up with low energy products. So Liam, would you label the delta H and the activation energy on the endothermic diagram, and Austin the activation energy and delta H on the exothermic? And we'll try to back some of the way where Aaron is taking.
You said label the activation energy?
Activation energy and the change in enthalpy. Where would you find that on diagrams? Because most people did okay. Most people did okay on the test with that, but occasionally I saw potential for struggle there.
These are yours.
From the energy of the reactants all the way out.
Is he right?
So for activation energy, that's right. You always go activation energy always, regardless of if it's endo or exothermic. You always go from the energy of the reactants to the top, energy of the reactants to the top. For delta H, you go energy of the reactants to energy of the products.
So it's here.
Here. And for delta H here, energy of the reactants to energy of the products. So, yep. So just put your delta H from start to finish.
So put it somewhere here. Sorry.
I would, no, that's okay. I would, like you have this dotted line here, so I would just use it to put delta H from there. So like seeing them both kind of together, it makes it kind of more obvious, because an endothermic reaction, those products start out at a comparatively low energy. They have to get all the way up to that activation energy before that reaction starts, and then they end up keeping a lot of that energy stored in their chemical bonds. With an exothermic reaction, it's not quite as intuitive, because the activation energy is comparatively smaller, right? You start out at a high energy state, so it's not such a large, hump to get over. But then, once it gets going, it's going to just give off energy to its environment and end up in a lower energy state. So, even though, if you look, the delta H's of these two are kind of similar, but the activation energies are very different. So what would it look like if I used a catalyst and on this situation and I changed the energy diagram? What would change?
The activation energy. You create like a shortcut.
A shortcut. So activation energy, of course, always in both diagrams would have to, let's see, what color can I really do that with? All right, I'm going to put on green. So the energy of the products and the energy of the reactants is what it is for a reaction, right? That they have the energy stored in their bonds that they're going to have at the given temperature that they exist. So you're always going to start here and here. The only thing that's going to change with the catalyst is going to be that activation energy. Right? So that's what a catalyst is going to do, is just decrease the activation energy, either by kind of increasing the concentration in a little area, or kind of introducing an extra step in the reaction, helping to form this, which then doesn't have as large a reaction activation energy as it would without being able to form that kind of middleman step, and then being able to form those same products in the end.
So, do reactions with catalysts give off less heat?
No, the delta H will be the same.
Okay.
But they just, like, are faster.
Mm-hmm.
Like, the hydrogen peroxide decomposes super slowly until you put that catalyst in, and then it's like, whoosh, decomposed.
Do we have to do that today?
We did that the last time. We're going to catalyze something else that's less dramatic, but more measurable, I guess. We can collect more data on this stuff than we could on the hydrogen peroxide. I guess we probably could. I don't know. It would be hard. This reaction, you can just visibly see when it gets to a certain point.
Were we gonna rerun the diluted test tube?
I wish. I didn't bring the stuff to rerun the diluted test tube, but we are going to dilute today's reaction and be able to see another reaction proceed at different concentrations. So hopefully we'll, and we're actually going to look at the effect of temperature on the same reaction that we look at the effect of concentration on. So hopefully in the end we'll see something a little more useful than Tums in acid. I mean, there's Tums, it's not even like maybe each pill has a different weight. They're not super careful. It's not going to kill you if there's a 1/10 of a gram more here or there, but it certainly isn't good for your experiment. What else do we need to talk about? Let me start thinking of final last week's question. So last week, your lab questions, it says discuss them out loud. I know you turned them in, but just in case. So last week we talked a little bit about this, that our yeast in peroxide was a heterogeneous catalyst because the yeast is solid. The peroxide was aqueous, and when it's a heterogeneous catalyst, of course, with a decomposition, the mechanism's a little different, but it's not necessarily attracting reactants to itself, but it's kind of complicated. So it appears like a heterogeneous catalyst, and in fact it is a heterogeneous catalyst, but the mechanism is, but you get to see that it does speed up by lowering activation energy. Today's will be a homogeneous. Last week, I don't know who all wasn't here, but we also did the Tums and acid thing, and so we had a control. We had one that was hot, one that was cold, one that was diluted, one that was crushed, one that was stirred, and we looked at the rate. And so, Austin, what would you expect to be the fastest reaction?
Homogeneous? I have no idea.
Well, like if we have some options like heated up, cooled down, diluted, stirred, crushed.
Crushed.
Crushed, okay. And frequently, crushed is nearly the fastest.
Mm-hmm.
This time, not so much.
Because of its increased surface area.
Yes. So crushing, and this is definitely big on the test, crushing is a good way to increase rate. So when you increase surface area, why would that increase rate?
Because it's not a solid anymore. It's crushed so that it takes up more surface area and its molecules are spread out, so it takes up more of the container.
Right. So if we have two test tubes here, and we put in a little tablet here, and we put in a crushed up tablet here, how much of the chemical is not accessible to the acid in the test tube when we don't crush it? A lot. Like it's like a package, right? Like if I touch just the outside of this container, I cannot touch very much of the entirety of it. If I stuffed my hand in there, I could touch a lot more, right? There's a lot of surface area that's inaccessible. But if you crush it up, of course, that exposes the things that are protected in the inside to the acid so they can quickly react. Whereas this, they're protected. Only the outside surface can react. So crushing increases rate by just allowing the chemicals to actually come into contact with each other. But crushing isn't the best way to increase rate. Why?
Because temperature, if you heat it up, affects it more.
Temperature affects it more. So why does temperature affect rate more than crushing, Lily?
Because it like increased temperature increases the energy, so the molecules are moving faster and they're a lot more likely to collide with each other and make the reaction happen than chemicals that are crushed and spread out but not moving as quickly.
Okay, so temperature has two effects. Right. It makes collisions more likely, and it makes them right. Collisions are more likely, and collisions are more forceful. So increasing the temperature is the best way to increase the rate of reaction, just like we talked about last week, because it makes collisions more likely and more forceful, right? For a chemical reaction to occur, you have to have two molecules collide so that their valence electrons can interact with each other. If they collide, but the collision's not forceful enough, no reaction will occur. If they collide and the orientation's wrong, they won't react. So they have to collide in the right orientation with at least the right amount of force, and they have to collide at all. And so with increased temperature, what happens to the way the molecules are moving around?
Speed up.
Right? So we're speeding up. If you guys are like running full tilt blindfolded in a room, are you likely to collide with each other? Yes. If you're walking around in a room, how will that change your collisions? Less frequent and less painful, right? So increasing temperature does two things to increase rate. Things like crushing and stirring and concentration, right? So if I had you walk around in this room versus walk around in the gym, where would your concentration be higher?
In here.
In here. Would it affect how hard you collide with each other if you had to walk at the same pace all the time? No. Only temperature affects the force of your collisions, but all of these factors affect the likelihood of collision.
I had a
So
question.
if you crush, if you stir, or if you increase concentration, of course decreasing concentration makes collisions less likely. But if you do these things, you increase rate by increasing collisions, but they're not more forceful, so temperature is still going to be the biggest factor. Lily?
I'm sorry, this is kind of nitpicky,
Yeah.
but for like you have written temperature, it makes collisions more likely.
Yeah, increased temperature.
Okay, yeah. That's
Yeah,
what I was gonna
decreasing
say.
temperature also
Does the
dramatically decreases the force and likelihood of collisions because things are really slowed down.
Well, we never talked about which one would make it go fast. We talked about which would change it the most.
Right. And today we're going to have low temperature reactions and higher temperature reactions, and some in the middle, and some diluted and some diluted more. And hopefully we'll see rate changing with all those factors. We won't look at crushing and stirring today. And last week's crushing thing was lousy. Crushing really increases rate, not as much as temperature, but usually more than stirring or nearly more than concentration, because it really is like starting out with a more concentrated